Okay, we're going to talk about escape speed. And escape speed is, again, I don't know if this is going to be on the AP exam, but it's very interesting and it relates closely to what we just learned about gravitational potential energy at astronomical distances. So any planet or any heavenly body with great mass has a gravitational field, a strong gravitational field around it. And in order to escape that planet's gravity, the object trying to escape has to have a certain velocity. So, when a rocket blasts off from the surface of the Earth, it has to have a certain velocity so that the Earth's gravitational field doesn't eventually bring it back around and cause it to start orbiting the Earth, in some kind of crazy elliptical orbit like a comet or something like that. So if you blast it off with less than escape speed, then what that means is the planet's gravitational field would still suck you back into it, and you would end up, landing either orbiting the planet or crashing into the planet, depending on how fast you were going. So escape speed is like the minimum speed something has to have to completely escape the velocity or the gravitational pull of the planet. So the minimum speed required would be when you get out to an infinite distance away. Pretend this is the opposite side of the universe. And when you get to that point, you just run out of velocity. So you have zero speed, and your gravitational potential energy is zero at that point as well. So basically, your UG is zero, and your K is zero. So if you got to this imaginary infinite point and you had any speed at all, then you would have wasted. You would had a speed above what you needed to escape. So you're getting to this imaginary infinite point with no velocity, and that means no kinetic energy. And as you remember, our gravitational potential energy formula for astronomical distances looks like this: mass of the spaceship times the mass of Earth divided by the center-to-center distance. So when that distance gets to infinity, that's a symbol for infinity, this basically goes to zero. So gravitational potential energy approaches zero as you get further and further away. So at this infinite point, it would be zero along with the kinetic energy. So since all energy is conserved, whatever I start with has to be the same amount of energy I finish with. Well, since I'm finishing with zero, I must start with zero. And you might say, well, how can you start with zero? Because I have kinetic plus gravitational potential at the beginning equal to zero. That means 1/2 mass of the spaceship times the speed, I have two S's now for some reason, times the speed of the spaceship squared minus G, mass of the spaceship, mass of the Earth, over the center-to-center distance at the beginning. Since I'm blasting off from the surface of Earth, my initial center-to-center distance is just the radius of the Earth. So this would be the radius of Earth. That would be zero. Okay? So now I substituted in the formula for these two things. I now have something I can actually solve to find the speed that something has to have to give me zero total energy at the beginning, with this big negative amount of gravitational potential energy and a big positive amount of kinetic energy. So let me just get rid of that. Notice that the mass of the spaceship appears in both of these terms, so I can cross that out. Sorry about that. I can cross it out, maybe not. Okay, we got it back. Since that appears in both places, I can cancel out the mass of the spaceship. So I'm left with 1/2 the velocity of the spaceship squared. I move this over to the other side, equals G, mass of the Earth, times the radius of the Earth. Solve for the speed of the spaceship. And I get the square root. I have to multiply both sides by 2. 2 universal gravitational constant times the mass of the Earth divided by the radius of the Earth. And that's an expression called escape speed. So when we went to the moon to escape the gravitational pull of the Earth and go to the moon that was out here, we had to be going, the Apollo spaceship had to get going at this escape speed right here. So let's just figure out what that is for the Earth. You know what the value of g is? It's 6.67 times 10 to the negative 11th. Mass of the Earth again is 5.98 times 10 to the 24th kilograms. And the radius of the Earth, so surface to center, is about 6.37 times 10 to the 6th. So figure all this out. I'll do that offline real quick, come up with a number. I get 11,193 meters per second, which is equal to, so there's 3,600 seconds in an hour, and there's 1,609 meters, about 25,043 miles an hour. And that's about how fast the Apollo aircraft had to go. So to find the escape speed for any planet or any moon or anything like that, you just need to know the mass of the moon or the planet and the radius of the moon or the planet, and you'll get the escape speed. Okay? Again, if, this is optional. If you want to ask me any questions about it, feel free. Okay?